Valence bond theory. In valence bond theory, bonds are formed between atoms by the sharing of electrons from overlapping atomic orbitals. For example, s orbitals can overlap, or p orbitals can overlap, or a p orbital can overlap with an s orbital. However, this will not account for all the structures that we can see and the molecular shapes. So we have to look at what we're going to call the hybridization of atomic orbitals. In this example of valence bond theory and ammonia, if we overlapped the 1s orbitals with the 2p orbitals, we would expect the bond angles to be 90 degrees. However, the bond angles that we find are 107.3, and as predicted by the valence shell model, they would be less than 109.5. Would not predict them to be 90 degrees. So to account for these differing bond angles, valence bond theory hybridizes or mixes two or more atomic orbitals to form a new set of orbitals. There are some rules with mixing. The mixing has to be two non-equivalent atomic orbitals, like an s and a p orbital, resulting in hybrid orbitals that have a very different shape from the original atomic orbitals. The number of hybrid orbitals has to equal the number of original pure atomic orbitals used in the hybridization process. So if you mix one s with one p, the resulting orbitals has to be 2, or else we wouldn't be able to accommodate the 4 electrons that we could accommodate originally in an s and a p separately. Finally, covalent bonds can then be formed by the overlap of hybrid orbitals with atomic orbitals in addition to atomic orbitals with atomic orbitals, and they can be formed by the overlap of hybrid orbitals with other hybrid orbitals. The first hybridization is the formation of what is called the sp hybrid. An s orbital is mixed with a p orbital. Note that when mixing, they both come from the same principal quantum number. Have to mix a 2s with a 2p. I don't mix a 2s with a 3p, for example. The result is two new orbitals called sp orbitals. This first balloon arrangement is a fairly large one. The second one gives us a little better feel for it over here with these sp orbitals. One pointing to the left and the other pointing to the right. When they are overlapped together on the same nucleus, as opposed to separately as seen up here in the diagram, we find that one orbital and the other orbital overlap each other in such a way that we get a 180 degree bond angle, the same as what we would see in a linear structure of the AB2 class. The sp2 hybrid is made by mixing 1s with 2p orbitals. The result is 3 new orbitals. The 3 new orbitals form bond angles of 120 degrees. These are the same bond angles that we saw in the trigonal planar or AB3 system. So you can see here that this type of hybridization and the trigonal planar go together. Next, we will mix an s orbital with 3 p orbitals, and we get the sp3 hybrid system. The sp3 hybrids, there are 1, 2, 3, and 4 orbitals, and if we associate that with the valence shell model, it's equivalent to the AB4 class, and the bond angles are about 109.5 degrees. For the ammonia molecule that we saw previously, the bond angles in the sp3 hybrid more closely fit with the 107.3 degree angles that we would see in ammonia. But again, we have to remember that a lone pair has greater repulsive forces to bonded pairs, and so the bond angles are slightly squished or reduced. To get the trigonal bipyramidal system, or the AB5 class, we need to mix 5 separate orbitals. We have run out of s and p orbitals, so we have to go to the third period of the periodic table, where the principal quantum number, again, is 3, and we're going to be able to mix in the third period S's, P's, and D's. So here, if we mix an S with 3 P's and a D, we call that sp3d hybrid orbital. Mixing 5 orbitals together, we get 5 orbitals out, and those 5 orbitals have the same shape that we saw in the trigonal bipyramidal system. The bond angle from the axial to equatorial position is 90 degrees, and the bond angle along each of the equatorial positions is 120 degrees. Finally, we need to be able to get a hybrid system that forms 6 bonds from the octahedral system. To get 6 bonds, we need 6 orbitals mixing together. The S, the P3, and D2 make the final class. These molecules form 6 new orbitals, and the bond angles are 90 degrees as predicted by the valence shell model for the AB6 class. The hybridization on the central atom and the Vesper models can be correlated with each other. When you have 2 total domains, which is the Vesper AB2 model, the hybridization is sp. There are 2 atomic orbitals mixed together, and the shape is linear. When there are 3 total domains, you have to have 3 atomic orbitals mixed for the hybrid, so sp2. The valence classes with this are AB3 and AB2e, trigonal, planar, and bent. For 4 total domains, you need 4 total orbitals, s, and 3 p's, and the classes from the valence shell model are AB4, AB3e, and AB2E2, the tetrahedral, trigonal, pyramidal, and bent molecules. And finally, on this slide, we have the 5 total domains. So we need 5 orbitals to mix together. The 5 that we're mixing are the S, 3 P's, and 1 D. the sp3d hybridization, and the Vesper classes are AB5, trigonal bipyramidal, AB4E, distorted tetrahedron, AB3E2, T-shaped, and AB2E3, linear. Finally, we're looking at 6 total domains. Need 6 atomic orbitals in the hybrid, 1 s, 3 p's, and 2 d's. The Vesper models are AB6, octahedral, AB5E, square pyramidal, and AB4E2, square planar. Now the question can be asked is, how do we create double and triple bonds? And how does hybridization play a role in that? Well, we have to ask what happens to those unhybridized orbitals. Here we see an sp2 hybrid, but if we have an sp2 hybrid and there are 3 p orbitals, there's 1 p orbital left, and that p orbital is here, the orbital in gray, and it is perpendicular to the plane where the sp2 hybrids are, and this orbital is available to bond with other p orbitals to create additional bonds. Here in ethylene, we see that the carbons are both sp2 hybridized, so they will have a p orbital which sticks up perpendicular from the plane of the sp2 hybrids, and these can overlap with each other and create a bond that has 2 lobes, one above and one below. The bonding that occurs directly between 2 atoms is called a sigma bond. The bonding that occurs as a result of p orbitals is called pi bonding. And basically what this does is it creates a stronger bond and a shorter bond and increases the electron density around the carbon-carbon bond here in ethylene. Here's another look at that double bond in ethylene. Here the pi bond is 2-lobed, and here showing the increased density of electrons between the 2 carbons. This is a nice little balloon model showing the sigma bonds between the 2 carbons and between the carbons and hydrogens, and then the pi bond between the 2 carbons. In a triple bond, typically the atom is sp hybridized, which leaves 2 orbitals, p orbitals that is, available for bonding to another set of p orbitals. The result is 2 pi bonds, one that goes kind of across and one on top and bottom. The result is much increased electron density between 2 carbons here, and the bond is also shorter. So when counting sigma and pi bonds, single bonds have one sigma bond, a double bond has one sigma bond and one pi bond, and a triple bond will have one sigma and two pi bonds. In the example below, sigma bonds, every bond has a sigma bond, so we can count those. 1, 2, 3, 4, 5, 6, 7 total sigma bonds. And then the double bond here also has a pi bond.